Okay, now section 9.5 binary trees. Binary trees. Binary trees. Binary trees. Binary tree is a tree that each vertex has no child or one or two child. Binary tree is a rooted tree that each vertex has at most two children, and each child is designed as either a left child or a right child. When a binary tree is drawn, a left child is drawn to the left child, and right child is drawn to the right. Okay. It is related with the Hoffman code. And this is an example of binary tree. Binary tree is a rooted tree in which every vertex has either no children, one children, or two children, and vertex of a vertex has one child. That a child is designated as either a left child or a right child, not both. A vertex has, if a vertex has two children and one child is designated as a left child, and the other child is designated a right child. Okay. So if a vertex has one child, it can be a left child or a right child. If a vertex has two children, then one child should be a left child, and the other child should be a right child. Okay, like this. If there are two, then one on the right, one on the left, and one on the right. Okay, in here, in a binary tree of figure 5.1, and vertex B is a left child of vertex A, and C is a right child of vertex A. And D is a right child of vertex B, and F is a left child of vertex E, etc. And Hoffman code, a tree that defines a Hoffman code, is a binary tree. Hoffman code. Hoffman code gives a binary trees. Okay. Here, a Hoffman coding tree of figure 10, moving from a vertex, a left child, to a vertex to a left child, corresponding to using the bit 1. Okay, bit 1 here. And moving from a vertex to a right child, corresponding to using the bit 0. So here 1, 0, left, right, like this. Okay? In the rooted tree, if it is a binary tree, then we can use the bit 1 and 0 in this manner, in the Hoffman code. A full binary tree is a binary tree in which each vertex has two children or zero children. 아까 함군 얘기하던 게 이제 그때 하고 얘기하던 게 full binary tree가 바로 이제 a binary tree in which each vertex has two children or zero children, like this. Okay, and it satisfies this condition. It has this property. If T is a full binary tree with I internal vertices, then T has I plus 1 terminal vertices and 2I plus 1 total vertices. This is a property of a full binary tree. If you count it, then you will see it does satisfies this relationship. And single elimination tournament, like what you see, like NCAA tournament, it also satisfies this relationship. And about binary tree, related the number of terminal vertices to the height. Okay, in a binary tree, the number of terminal vertices to the height. Okay, if a binary tree of height h has t terminal vertices, if this is a height 1, 2, 3, 4, height is 4, and it has 1, 2, 3, 4, 5, 6, 7. 7 terminal vertices. Then this relationship, it is inequality hold. Log of t is less than or equal to h. Log of 7 is less than or equal to height 4. And that's what it says. So if 여기서 이제 로그 대신에 이제 파워를 여기서 취하면 로그 양쪽에 이제 로그를 벗겨주면은 그러면은 이제 anyway the log of 7 is less than or equal to 4. That's what this graph shows. Anyway, so there you can find some relationship of on the binary trees by using the number of terminal, degree, and height. Here also same thing. In this case, also it satisfies that properties. Anyway, inequality. Next, here, binary search trees. If data item here, binary, here, binary search. Binary search tree is a binary tree T in which data are associated with the vertices. The data are arranged so that for each vertex V in T, each data item in the left subtree of V is less than the data item in V. And each data item in the right subtree of V is greater than the data item in V. Okay, let's hear about the binary search trees.
Well, hello Internet, and welcome to part 13 of my Java algorithms tutorial. Today we're going to talk about binary trees. More specifically, I'm going to tell you what a tree is, what a binary tree is, how to create nodes, how to add nodes, how to traverse a tree, and how to find specific nodes. In the second part of this tutorial, I will show you what is considered to be quite complicated, which is how to delete nodes. So we have a lot to do, so let's get into it. So whenever you're thinking about trees, I know some of you guys already know this, but I'm going to review it really quickly. Basically, the top node of a tree, and you can see it looks kind of like a tree structure, is known as the root. The lines that connect all of the nodes thereafter are known as paths. Parent, a lesser value than the parent on the left, and this is known as a left child, and a greater value than the parent on what is known as the right child. You still have leaves, of course, and even though the maximum number of children is 2, you do not need to have both children in a binary tree. So what is an unbalanced tree? Well, normally random data isn't going to create what is known as on average, just to get down to it, a tree is more efficient. The constructor do its work, and then we want to check if this is indeed the root element for our tree, and if it is, we're just going to throw a new node in there and be done with it. However, else, if it is not, we're going to create ourselves another node, and I'm going to call this the focus node because this will be the node that we are focusing on. And I'm going to set root as this node because, of course, we're going to start with root as we traverse through our tree. I'm going to show you a couple different ways to traverse through trees. And then the future parent for our new node, we're going to just set that up as well. And then we're going to go while true, which is going to create an infinite loop, of course, which we're going to have to jump out of at some point. And then, of course, like I said before, we're going to set our parent as the focus node, which we already know is the root, because that's where we're going to start. Then I'm going to say if key and add node like that, and paste those in there, the node we're looking at. So it's just going to print it out. Next part of the tutorial, I'm going to cover the more complicated topic of how to delete nodes. Please leave any questions or comments below. Otherwise, till next time.
Okay. Okay, anyway, whenever you need, you can go back to see what the binary search tree means and how you can generate code, and how can you use. And it also has motivations for that. Anyway, for a form of binary search tree for a world mathematics, physics, geography, geology, meteorology, geology, psychology, and chemistry. And then start from the mathematics, and then physics, then the geography, and then geology, then meteorology, etc. So this is the way constructing a binary search trees on the academic subject. It can be used in that way. Alphabetical order. Yeah, he used here. We use the alphabetical orders. LMN, O, P, Q, R, S, T. Anyway, alphabetical. This is algorithms. And here, example shows our old programmers never die. They just lose their memories. And this sentence can be represented in a binary search trees. With the algorithm, it can be arranged in this way. Then the rules you can read. The old programmers never die. They just lose their memories. And that's the way of readings. I will show how it works. Constructing a binary search. This shows how we construct the code. How to construct binary search trees.
In some past videos, I've talked about binary search trees and how to put them together. However, I took a data set that was very well structured, and so the tree was nice and balanced. And then in some of our other videos, we went over red-black trees and how to show you how that works. So the first element, and then it will put 7 on the right-hand side, right next to 5. After that, we have a 1. 1 is less than 5, so it goes to the left. And right here we have a very nice basic tree structure. We have our root node. We have 1 being the item or the node to the left, 7 to the right. So far everything is normal. Now we're going to add 15. 15 is greater than 5. It's greater than 7, so it needs to go all the way to the right. Now I'm just going to start adding some more in order in the array. So we have to treat it as such, and we have to add. We see that it's great. 2 nodes are actually the same value. 1 is directly a descendant of the root node, and the other one is all the way here. Now it is a 3, and that's greater than 1, greater than 2, so it gets pulled here. And so given this data structure here on the right-hand side, this is what a visual representation of the tree would look like. So you can see it's not balanced, however, it is properly structured. If you were to run a search on this, so say that we wanted to find a binary search tree given an array.
Okay. Anyway, this shows how we construct a binary search trees. And this is example. And also here is a summary of Huffman coding, and the algorithm represent the Huffman coding algorithms. Anyway, here this 3 traversers, 3 운행, 3 traverse, and this. The breadth first search and depth first search provide ways to work a tree. That is to traverse a tree in a systematic way so that vertex is visited exactly once. Okay. There is just 3 additional tree traversal method. That's why I skipped. I went fast. Now we can explain how these search algorithms work. 그러니까 이게 여기서 보면은 아까 배운 breadth first search 또 depth first search가 이제 이런 버틱스들이 있을 때 어떤 순서대로 이게 지나가면 한 버텍스들을 이그젝트리 한 번씩 지나갈 수 있느냐, 그게 어떤 패스가 효과적인 패스냐, 그걸 찾는 방법이 세 가지. 거기가 이제 아까 했듯이 그 프리 또 인워드 그 다음에 포스트 워드 그 알고리즘 프리오더 또 인오더 포스트 오더 트래버설. Yeah, so there are three additional tree traversal method will be introduced in this section. So procedure for systematically visiting every vertex of an ordered rooted tree are called traversal algorithm. Yeah. Here we will explain pre-order traversal and in-order traversal and post-order traversal. First, pre-order traversal. It can be found in here.
That it's important to
But basically it's very simple. This algorithm shows pre-order traversal is start from here and then go to left first and then visit the next one, move to the right side. So it goes like this. I will, for example, this process show like this. Pre-order algorithm gives us a path that starts from here, from A to B, B to C. Then it's all done. Then go to the right, the nearest. Then go to the E, and it's all done here. Then go to the right, which is not used first. Then go to the left first, then right. So this way, the path, the pre-order gives us this path went through all the vertices. But in order, I will explain in order later. Here. In-order transversal and post-order transversal are obtained by changing the positions of line in algorithm 6.1 and pre, in, and post refer to the position of the root in the traversal. That is, pre-order means root first. Pre-order algorithm, traversal algorithm start from the root, and in-order means root second. Post-order means root last. That means it's in order traversal, we start from here, from the very left, and then go like this. I will show it in here. Post-order, where is it? In-order. In-order, here. Here. This is in-order. In in-order, if you have a root like this, you start from the left and then go second, 1, 2, and then third, fourth, fifth, sixth, 7, like this. In pre-order, as I mentioned, start from the root and 2, 3, 4, 5, 6, 7, like this. And post-order, you start from the left and end at root. So start from the 1, 2, 3, 4, 5, 6, 7, like this. That's the order. Got it? Do you see? And this, so pre-order, start from the root and then finish up all the left, then go to the right and end at here. In order, you start from the left and then up and down to be ended at here at the last. Post order, you start from the left hand, left bottom, terminal, then go through left, up, left, right, up, and ended at the root vertex. All these algorithms, the post order and the 3 traversal algorithms are explained well on here. I looked at
In our previous lesson, we talked about level order traversal of binary tree, which is basically breadth first traversal. Now in this lesson, we are going to discuss these three depth first algorithms: pre-order, in-order, and post-order. I have drawn a binary tree here. Data type filled in the nodes is character. Now as we had discussed in earlier lessons, in depth first traversal of binary tree, if we go in one direction, then we visit all the nodes in that direction. Or in other words, we visit the complete subtree in that direction, and then only we go in other direction. In this example tree that I've drawn here, if I'm at root and I'm going left, then I'll visit all the nodes in this left subtree, and then only I can go right. And once again, when I'll go right, I'll visit all the nodes in this right subtree. If you can see, in this approach, we are reducing the problem in a self-similar or recursive manner. We can say that in total, visiting all the nodes in the tree is visiting the root node, visiting the left subtree, and visiting the right subtree. Remember, by visiting a node, we mean reading or processing the data in that node, and by visiting a subtree, we mean visiting all the nodes in the subtree. In depth first strategy, relative order of visiting the left subtree, right subtree, and the root can be different. For example, we can first visit the right subtree, then the root, and then the left subtree, or we can first visit the root and then the left subtree. I'll make a call to pre-order, passing it address 200. For this call, root is not null, so we will not return at first line in this function. We will go ahead and print the data in this node at address 200. I'll write output for all print statements here. And now this function will make a recursive call. Execution of this particular function call will pause. It will resume only after this will also finish. Even for pre-order 400, both calls have finished. In in-order traversal, my base case C, then there was one function call corresponding to each node where we were actually visiting that node, where we were actually printing the data in that node. So running time should actually be proportional to number of nodes. There is a better formal and mathematical way of proving that time complexity of these algorithms is big O of n. You can check the description of this video for a link to that. Space complexity, as we had discussed earlier, will be big O of h, where h is height of the tree. Height of a tree in worst case will be n minus 1. So in worst case, space complexity of these algorithms can be big O of n. In best or average case, height of a tree will be big O of log n to the base 2. So we can say that in best or average case, space complexity will be big O of log n. I'll stop here now. In coming lessons, we will solve some problems on binary tree. Thanks for watching.
Okay, so yeah, this shows briefly the three type of traversal algorithms, and yeah, pre-order, post-order traversal, and in the post-order traversal, the root vertex will be the last destination of the root, like what you see: pre-order, in-order, and post-order traversal, from left to right and root at the end. Pre-order, start from the root, left to right. In order, start from the left, then root, passes to the root, then ended at the right. And these are the example. In this traversal example, if you have a tree like this, if you use a pre-order algorithm, he will give you this path. From start from A, B, E, J, then K, N, O, P, then F, then C, then D, like then H, I, like this. Okay? In order. And so the same examples. Pre-order, in orders. Here, the variables are introduced. Next, decision trees and minimum time for sorting. Yeah, decision tree, here's the definition for the decision tree, and binary tree containing an algorithm to decide which course of action to take. then used to specify algorithms then to obtain lower bound on the worst case time for sorting decision tree. That's the definition of decision trees. And 5 coins puzzles are one example of the decision trees. And there are some explanation on that 5 coin problems, and which we're gonna skip it. It is related to the computer project. Here, the last. This is the last section in chapter 9 that we will cover: isomorphism of trees. Graph isomorphism, we have learned in the earlier chapter 8. And 2 graphs are isomorphic if and only if they are identical except for their node names. Okay? And now we're going to define an isomorphism of trees. Here, I think 3 isomorphisms. And this, I think we can. Here, this 5 minutes explanation.
아직도 가그린에 색소가 있다고 생각하시나요? 이렇게 투명한데?
Hello friends and welcome to another tutorial on Geeks for Geeks. In this video, one of them can be obtained from other by a series of flips. That is, as well, we compare the data of n is null.
Since
So we
this
need
is a simple concept, so I'll explain it. Here, for example, the function f from a vertex set of the tree T1 shown in this figure to the vertex set of the tree T2 in here, defined by A goes to 1 and B goes to 3 and C goes to 2 and 4 goes to D goes to 4 and E goes to 5, then this graph and this, then this function f is a one-to-one and onto function that preserves the adjacency relation, which means 2 trees are isomorphic, isn't it? Suppose there exists a one-to-one and onto function that preserves the adjacency relations, which have the same adjacency matrix, then that 2 graphs are isomorphic. So these 2 are isomorphic trees. Okay, but these are not isomorphic trees because here this vertex, this vertex has what? The 3 edges. Degree. So, but degree of vertex is 3 here, but there is no vertex which has degree 3. So they are not isomorphics. But this and this are isomorphic, and this graph and this graph is isomorphic. They are, but these are not isomorphic. Here it has a vertex of degree 4, but there's no vertex which has degree 4 here. And for the case of 5 vertex, the tree with the 5 vertices, there are 3 different type of non-isomorphic trees. For example, here, when we have one vertex, there is 1 trees. But when you have 2 vertices, then you have 1 isomorphic graph for 3 and trees. We have this. But when you have a tree with 4 vertices, we have 2 different non-isomorphic graphs, trees. For n is equal to 5, then we have 3 different type of non-isomorphic. We have 3 non-isomorphic trees like this. Okay. For finding I find the number of all non-isomorphic trees for the large number n is not an easy problems. And isomorphic definition of isomorphic is that if there is exists a one-to-one and one-to function f from a vertex set of T1 to vertex set of T2 satisfying the following two properties. Okay, vertex Vi and Vj are adjacent in T1 if and only if the vertex of f of Vi and f of Vj are adjacent in T2, and f of R1 is equal to R2. If it satisfies this, then we call the function is an isomorphism, and these two trees are isomorphic. For example, in this graph T1 and T2, if we define f in this way, then this f satisfies two property, which was noted. So it is an isomorphism, and these two trees are isomorphic. But in this case, we cannot find an isomorphism for these two trees because there's no such functions. In here, we have here we have 1, 2, 3, 1, 2, 3. Here 1, 2, 1, 2, 1, 2, 3. Here these two graphs are not isomorphic because the root of T1 has degree 3. Root has degree 3, but in this graph, in this tree, this root has degree only 2. So these two graphs cannot be isomorphic. And there are 4 non-isomorphic rooted tree with 4 vertices. 1, 2, 3, 4. These are 4 different type of two non-isomorphic rooted tree. And what else? Yes, some isomorphism. And also, these two are isomorphic. And these two are not isomorphic because here V1 the root has only a right children, but W1 the root here has no right children. It has only left children, so they are not isomorphic in the binary trees. In binary trees, they are not non-isomorphic binary trees. Here, the definition for the isomorphism in a binary trees, we had 2 more conditions. Left goes left, right goes right. And these two are isomorphic trees, but they are not isomorphic binary trees. There are 5 different non-isomorphic binary trees with 3 vertices. These are the examples. The interesting thing is there are n non-isomorphic binary trees with n vertices where Cn is the nth Catalan number. Isn't that interesting? Catalan number that you have learned in the earlier is exactly represent the number of non-isomorphic binary trees with n vertices. Here, can you see? Pop up here. Let's see Catalan numbers. How it is related with.
As a poster child for the application of generating functions, next we're going to take a look at the Catalan.
Here.
You can have 1 on one side and 2 on the other side in 4 possible ways. So again, same number sequence, again, satisfies the same recurrence. If you've got k nodes on the left, you're going to have n minus 1 minus k nodes on the right, and you can try all possibilities on either side. So it's got to satisfy the recurrence where t is n is equal to the sum for all k up to n minus 1 of tk, tn minus 1 minus k, plus a delta term to make it true for 0. Catalan numbers. Here's another one. How many trees within nodes? A tree is a node connected to a forest of trees, to any number of trees. So it's not restricted to be just 2. And again, we'll talk in detail later in the course about trees and binary trees.
So
now
he gave a
that
good
inner
explanation on those concepts. Yeah. So catalog number can be used to categorize the non-isomorphic binary trees. And this is algorithm to testing whether the 2 binary trees are isomorphic or not. Yeah, you can easily find the code for this to check your 2 binary trees whether they are isomorphic or not. And this is the time. This shows the algorithm complexity. Like I mentioned, the theta of n is the worst case time of algorithm, 8.13. And yeah, you have seen the catalog number, how it was counted. And yeah, this is, we went through it once before. And I think that's the end of the chapter 9. Okay, any question on trees in chapter 9?